For this presentation, Chris Wolfe, who is an automation engineer and a space enthusiast who works with the Space Development Network, is going to talk to us about lunar roads.
As mentioned, my name is Chris Wolfe. I do QA and systems integration at SiriusXM in my day job. Space enthusiast and author. I work a lot with Doug in the Space Development Network on questions and special projects. Usually I focus on Mars, but as we all know, the moon is a lot closer these days than it's been in a very long time. So the subject today, we've already heard from quite a few people who know rather more than I do about properties of the lunar regolith, dust mitigation, and things like that. So we're going to focus on one specific topic, which is roads. So I'll mention there are a few places where I'm quoting or relying on theories and stating them as if they're facts. So don't just assume that everything I say in definite terms is true. Some of this is subject to further discovery. That's just for convenience of communication for now. Right, so roads connect places that people might want to travel between. Right now we don't need any, but very soon we will. You know, for an initial polar base, that's probably closer to paths than roads, something people can use to travel between landing pads, habitats, PV arrays, maybe reactor sites someday, research sites. Longer term, as we expand our presence to more points on the surface, it may be appropriate to build much longer roads to make travel easier. And most of the potential propellant materials are near the poles, but a lot of the places we might want to explore or visit tend to be quite a distance from there. So if we were to set up a base and landing pads and propellant production and all of that at the poles, and then have a system of roads to connect the points we're interested in, we can keep our travel confined to one place. And that also, by establishing roads or designated places to drive, that keeps us from leaving wild rover tracks all over the lunar surface, because once they're there, they're there. They're not going anywhere. All right, so we're going to talk about hazards, the goals that we want to address, and the methods that we might go about doing that. Dust, we've heard quite a bit about. It's sharp, it's tiny, it gets everywhere, it's very, very abrasive. They're so small that they're subject to electrostatic effects and plasma interactions that can loft them for hours or days. When they come back down, they can stick to PV cells, to rovers, cloth, anything, everything. And once they're there, they're very difficult to remove. Anything we can do to reduce the distribution of dust will help in cutting our maintenance demands, extend the lifetime of hardware, and generally be safer for people to be around. Rough terrain, we've got low gravity. Even a little bump or a rise can put a lot of sway into a vehicle. There's a pretty sharp limit on safe speeds. I've got some footage. Sorry, I can't seem to copy out of this. I've got some footage from Apollo 16 that you might find interesting. It's been, sorry, minor technical difficulties. It's been rescaled and resampled, which looks great. I'm going to paste these links into the Zoom chat. I would share them directly through the meeting, but video doesn't really work that well. Okay, we're good. Right. So pretty much the whole surface of the moon is a massive overlapping field of craters. Flat areas are kind of rare, and when you do find them, they tend to be in the bottom of craters, which are kind of hard to get to anyway because of the pretty steep walls. So a lot of the places we're interested in getting to have wavy or ridged terrain. If we want to be able to travel over that efficiently, our best bet is to try and do some leveling at least. And also the surface layer, the top 10 centimeters or so of regolith tends to be very loose. It kicks up as dust. It doesn't offer very good traction. Not that there's great traction anyway due to low gravity. Particularly anything that has to deal with earth moving or that works using a reaction force like a bulldozer blade, those are much more difficult to operate in lunar gravity than they are in Earth's gravity. Right. And then also, of course, there are boulders and other big obstacles. You know, they're fairly common. They make autonomous pathfinding difficult. They provide visual clutter that can cause trouble with pathfinding algorithms. Now, some of them we can move, some we can ignore and just drive over. Others, we have to avoid them, go around, take a longer path. Which ones are which kind of depends on your vehicle's suspension, your load limits. Now, how sturdy did you build your rover? Can it actually take a field of fist-sized stones at 40 or 50 kilometers per hour without issues? Now, of course, if you have a perfectly smooth, flat, level surface, you can drive an awful lot faster. So there are trade-offs there between speed and complexity and mass and durability and all of those things. Right, those hazards out of the way, we've got some goals. A good road should minimize all of those problems and more. It should reduce or eliminate dust from travel. It should be as straight and level as we can manage it. It should allow for fast, safe travel that's easy to automate. They should go wherever people need to go, so we're not laying down new tracks in untouched regolith. Of course, we want them to be cheap, fast, and effective, which means we need to compare factors like mass from Earth, on-site human intervention, mechanical complexity, all of those typical engineering trade-offs and challenges. So in the near term, we're talking about the paths that vehicles will take between the surface infrastructure, you know, landing sites and HABs and so forth. And the first sites are probably going to be near the lunar South Pole in permanently shadowed craters or near them. So they'll run along crater rims and then start to branch out to other places of interest as the site grows. Right, that image is a screen capture from one of the videos I linked. It's the Apollo 16 Grand Prix. They did a couple of minutes of footage for an engineering analysis of the lunar rover, and it kicks up quite a bit of dust. An action like this would cover an autonomous rover in dust pretty quickly. It would obscure solar panels, it would get into any moving parts and abrade them. And I'm expecting that most of the vehicles we'll be using near term on the moon with people involved will have, we'll use battery power and just recharge from time to time. But we still want to limit dust exposure to rovers' mechanisms. And the same applies for EVAs. Whenever possible, we want astronauts to walk on a prepared surface instead of loose dust. And there's always going to be some things that you need to do to walk off the path, to go do, to examine things or take samples or whatnot. But daily maintenance, hopefully not daily EVAs, but routine maintenance around the base itself shouldn't involve a lot of dust contamination. And we need both prevention and remediation, but the more prevention we can manage, the more life we get out of our equipment and the safer it is for people. We want to be able to reduce travel times so we can get the most out of the people and resources we have. Roads that have been leveled and have their obstacles removed give us short paths, easy autonomous pathfinding, and higher safe speeds. Autonomy is especially important because crew time is one of the most valuable commodities on hand. A crew member's time is far more valuable running experiments or fixing complex mechanisms or exploring than just driving rovers from point to point or hauling dirt and ice for industrial use. We're already capable of levels of autonomy that can deal with obstacles, but it's complex. The software is difficult to validate, and we're going to have limited opportunities to do that kind of validation in a reasonable lunar environment or simulation. Contrast with autonomous vehicles or partial self-driving vehicles on Earth, where the cars themselves and the software can run for thousands or millions or billions of miles of data collection. So it'd be better if we could rely on a simpler algorithm that's well understood and predictable, but can still handle navigational tasks like driving around on prepared surfaces in predefined road networks. Roads let us cut down our footprint on the lunar surface. Every bit of that surface has information that might be useful, so we should limit how much of that information we destroy, sample as much of it as we can beforehand. Once we know more about how much we know and how much we don't know, we can make more informed decisions about how much of the surface it's safe for us to modify. Until then, it would be best if we can minimize our disruption, keep it contained. And outside of exploration tasks that actually require it, we shouldn't be laying in new tracks, new footprints anywhere outside of the sort of construction area or footprint of the base itself and any associated facilities. There's very little natural erosion on the moon. Most of it's from micrometeoroids and dust deposition. So any mark we make is going to be there for a very, very long time. And longer term, someday people are going to want to visit historical sites like the Apollo landings. We know that we don't want people walking right up to the things and touching hardware. We don't want to be landing rockets anywhere nearby and sandblasting things. So a road network and some kind of clear mark saying, you know, step this far but no further, take your pictures here and then go away. That can help us protect historical sites and other places of interest. The one exception to that, though, if I could make a suggestion, would be Surveyor 3. Apollo 12 landed fairly close to that lander to take samples and look at what the effects of space weathering and a nearby landing would do to the surveyor. I think if we were to go back, we could take another set of samples and compare the samples taken in the 60s with the ones 50 or so years later and see what has an additional 50 years of exposure to the lunar environment done. I think that would be some very valuable information. So the next question is, how do we build a road that satisfies our goals? And the ideal approach would only need simple machines, no consumable supplies, and is fully autonomous, or it could be teleoperated, while still being fast to build and leaving an excellent surface. Now, we're almost certainly not going to get all of those in one solution. And even if we could, we're not getting it anytime soon. So let's look at a few methods and see what's possible. I'm going to be mixing up operations with approaches, so I'll apologize in advance to anyone who actually has experience with earthworks or road construction. Just note that some of these slides describe machines or steps that can be taken, and others describe ways that those steps could be combined. And I'll try to get into that as I go. image is a screen capture from Doug's animation on the space development website. There will be a link at the end of this. This is for in-place compression, which is basically a roller wheel or a vibration mat or some other thing that physically compresses the surface regolith with weight and vibration. The approach is fairly simple. It does have moving parts, but they're fairly few. It takes quite a bit of mass, but some of that mass can be regolith itself, local rocks. So we don't necessarily have to ship it all in. And ideally, this would be an attachment that could fit onto an existing rover and drive around, making a compressed surface. It's quick, it's simple. The quality of the road surface is not as good as some of the other options, but this would be a good start. So some of the drawbacks to this approach are that you, depending on whether the rover has any other attachments, you might have to go around some of the bigger rocks. You'll have a limited ability to level out terrain. And when you're finished, the road surface probably won't reduce dust as much as some of the other methods. So this might work best in combination with some other tools. So one thing to mention too is that the moon is in a hard vacuum. Even though that top surface, 10 to 15 centimeters of regolith, is only about half the density of the actual grains themselves, when you compress it, there's no air trapped in the grains. There's nothing to blow out. So as the roller moves over, on Earth, if you had fluffy soil and you were compressing it really hard and quickly, you might expect to see some dust blow out of the sides and make a mess all over the place. That doesn't really happen in a vacuum. There's no gas to transport those particles out. So you only kick up anything that sticks to the drum itself. Sweepers, kind of like street sweepers, you know, bristle rolls, a broom or something like that. Those work similar to a roller. You know, you're using them to move the surface regolith, the loosest stuff out of the way so that you can travel on the hard pack underneath. And the depth depends on where you are on the surface. It tends to be deeper near the rims of craters, shallower in the mares, but there is a layer under there that's so hard that it's difficult to break through with hand tools. Just digging out to that depth would give you a reasonable surface for driving. You'll cut down dust quite a bit. The drawback, though, is that you're not really leveling anything. You're just scooping the loose stuff out of the way. So you still have the same underlying undulations in the road surface. It would be fairly rough. One benefit to something like this is that you can configure them to push stuff out of the way or to collect and harvest things and store them, depending on which direction the opposing rollers move. These work with minimum net thrust, so they don't throw the rover around. They don't require a huge amount of mass to work effectively, but they do tend to throw dust everywhere. It's a fairly messy process. You're going to have a lot of contact surfaces touching dust and then moving fairly quickly. So this isn't really something you'd want to do in an established facility or base. Material-wise, you'd probably start off shipping bristles. They'd be replaceable on little mechanical hooks. But over the long term, if this turned out to be a worthwhile idea, you could use bamboo or plastics, either of which could be produced locally. You've probably seen a few pictures of this rover today. It's great. This is the Pisces rover with a dozer blade attachment on it. We're pretty much all familiar with this. You're moving the material around. It's a little more flexible than something like a sweeper or roller because you do have the ability to cut down high spots and fill in low spots, try and level things out as best you can. But ultimately, you're trying to dig down to hardpack and leave you with a good surface. The real challenge with this is thrust. Earth-moving machines rely on friction with the ground. They build up inertia, and move soil while staying relatively stable. In lunar gravity, that friction force is greatly reduced. So even with a huge amount of mass on top, it's hard to do operations with a blade like this. You can do it. You take shallower cuts, you use a narrower blade, move slower in some cases. In other cases, you need to move faster, but it's possible. It's just difficult. Gardening. So this is more of an approach than a device. The lunar regolith, about 10% of it is made up of grains that are 0.5 millimeter or bigger. I mean, you might call it sand and small gravel. If you were to excavate it and then run it through a sieve and separate it by size, you could put the finest dust back in the bottom, compact it, and then lay the sand and larger grains on top. So that gives you all local material. All you're doing is gardening it, rearranging it according to size, putting the biggest stuff on top so that the top surface no longer kicks up when a rover drives over it or someone walks on it. This should leave us with a pretty good surface. It's complex. It's going to take multiple pieces of equipment, which of course means there are maintenance concerns. But if we're already running a fairly large industrial outpost that's handling a lot of regolith routinely, we may already have all of those pieces of equipment on site. Gravel is an option. It's just like the previous idea. You basically level and compress things and then coat the top in crushed rock. Of course, you have to get the rock from somewhere and then crush it. So if you don't have a ready supply of cobbles or boulders, if you're not landed right next to a boulder field, this probably isn't a great option. But if you do have the local resources available for it, it may be simpler just to run rocks through a crusher and then deposit them than to do almost anything else. Pretty much anything industrial is going to involve rovers that carry material from point to point. So as long as they can deposit it in a fairly smooth layer, you can use your existing equipment to do something like this. So, and I mean, a gravel surface should be durable, pretty reliable. You know, we don't have to deal with freeze-thaw cycles. I mean, we do, but there's no groundwater to disrupt things. There's no mud. So a gravel road like this should last a very long time. And again, Pisces road. Bricks or tiles. Interlocking tiles of compressed or sintered regolith get deposited as a solid surface. Functionally, it's similar to a gravel road, but instead of using crushed rock, you're using regolith, which is much, much more abundant and easier to pick up. So compress and sinter those and then deliver them to wherever you need them and deposit them. This works best if you do at least a little bit of compression and leveling of the subsurface. But this lets you get away with crossing fairly deep craters as long as you can fill them in. You don't have to compress the roadbed itself super hard as long as the tiles are in good shape. And of course, the same approach is being investigated for making landing pads. Since they're durable, they can withstand rocket exhaust, and the raw materials are mostly on site. And of course, if you're sintering these with microwaves or resistance heaters or something, the power requirements are pretty big. If you have solar concentrators or a solar oven or something like that, then maybe this would be a better option. I guess it just depends on what kind of energy resources you have on hand. And also, if you're trying to make a really high-speed road and you're doing banking and turns and things like that, the tile shapes can get very complex if it needs to be tight-fitting and accurate. It may be that we don't need that level of accuracy on the moon because we don't really have high winds or water infiltration that can expand as ice. So some of the fine details of road building here on Earth don't apply just because there's no water. You can try sintering in place. This screenshot is from an experiment, an art experiment actually, a device to sinter things out of sand just using a giant Fresnel lens. Something similar could be done on the moon. Whether it's a microwave or a solar concentrator, you can use something like this to make a hard, rough surface that's kind of like, almost like a continuous cast concrete, just the surface quality wouldn't be anywhere near that good. It's very power intensive. I mean, ideally, you would also pair this with some kind of subsurface preparation, like compression or leveling. The behavior and performance of sintered materials depends a lot on regolith composition and tight temperature control. So not all regolith will be suitable for this as is. Some areas you might need to lay insulation over the top afterwards to slow the cooling and prevent cracking. In others, you might need to bring in material from nearby. Maybe you need to bring in some additional crushed basalt to make sure that it sticks fairly well. And as you can see from that image, it is possible to melt silica with a lens on Earth. So it is definitely possible to reach those temperatures on the moon just with direct solar concentration. It can be fairly complex. Microwave works well because due to the gardening processes that create regolith in the first place, there are nanophase iron particles scattered throughout the regolith, and those work very, very well at absorbing energy from microwaves and heating up the material itself. Mats. This is another idea that started for landing pads, which is bring with you a carbon fiber mat and pin it in place. And for that purpose, it would work. It would be fairly effective. They wouldn't actually need to be staked down or anything, but for something like a road, you would need some way to stabilize and attach them to the ground. Something like this could be deployed very quickly. It is, of course, pretty massive intensive because you have to bring the mat with you from Earth, unless you have a carbon fiber manufacturing facility already on site. You know, a lot of the tech has already been done. There have been studies on weaving techniques and heat resistance and abrasion and all of that. And also something like this is redeployable. So unlike a lot of the other processes, if you were to put down a mat road and decide you no longer need to access that resource or investigate that site, you can move the mat to a different location and reuse it. Resin. You take a vacuum adapted resin and spray it over the road surface and mechanically fix the grains together. And it's kind of like sintering, only using a chemical agent instead of heat and melting the grains, which means it works with any composition of regolith. You could use that anywhere on the surface. It's low power requirements. It's fairly versatile. And the main drawback, of course, is you have to source the resin from Earth. It would be possible to use the same approach to make blocks or tiles instead of sintering. And similar advantages and drawbacks to a tile road, except that in this case you'd also be importing the resin. I see that there are quite a bit of good questions coming in. I just want to kind of get through all of these real quick before we turn into that. Concrete, of course. Regolith makes sense as an aggregate. It's fine-grained. The cement component could be sulfur. That's been talked about quite a bit. It could be alumina-based, baked, crushed. Regolith can be turned into a decent cement. It's possible we might do continuous cast like we do roadways here on Earth. It's a little more likely that we might prefab large tiles, in which case it would be, again, kind of like a larger scale tile road. And that also curing a concrete in a vacuum under the temperature conditions on the moon can be very challenging, which is another factor in favor of us making big blocks, because then we can carefully control how well they cure. You know, if they're curing with water based, then we can use steam instead of soaking it in water. I know a lot of people don't want to use a water-based concrete for that, and for good reason. Water's scarce, and we should try to conserve it as much as we can. But in small amounts, that may still be viable. And that's my coverage. I mean, the best choices for road building is going to depend on specific conditions and locations, our tech level, how much travel we're looking at from point to point, all of those things. I tend to think the most viable options are going to be those that use general purpose rovers with interchangeable tools and don't have any significant consumable mass. But that remains to be seen. There may be cases where we actually need to bring a fair amount of mass from Earth in order to deploy something quickly. All right. Questions?
Thanks, Chris. Appreciate that. Great presentation. We've gone a little over, so we got time for just a few questions. Ben Stanley asks, do you have ideas for keeping roads clear of regolith kicked up by landings or takeoffs, or for cleaning them off?
Ideally, we would have landing pads that prevent any dust showing up, but you probably could adapt a sweeper design to go and clean them out periodically, unless we're able to work out some kind of electrostatic approach.
All right, I'm just scrolling down here to see, because there's some discussion back and forth between sintering and compression, and I think you covered most of that. Yeah,
so for established long routes, wouldn't some kind of suspended cable car system be 100 times easier to set up? Probably. That's a bigger investment, so you'd need quite a bit of traffic for that to be worthwhile. I think in the process of establishing the existence of that traffic, you'd probably start with a much more basic road, and that in turn would make it easier to deploy pylons and suspended cables.
Yeah, that makes sense. Where would the resin come from? Transport or harvesting?
Almost certainly transport. I think a lot of the resins that have been considered for this are urethane based, and I'm not aware of anyone working on urethane production on just local resources. I'd be happy to be proven wrong about that, though.
Okay, Manny Pimenta mentions that we need to consider radiation shelters at regular intervals, maybe within an hour of travel.
That would be great. I mean, longer term, I'm kind of the idea that we'll end up with a lunar rail line at some point if we're really serious about sustained investment in the moon, and that would be entirely underground, or at least buried under regolith. So you'd have radiation shielding for the entire trip. Until we get to that point, though, yes, radiation shelters, charge stations would be an excellent point for that. If we're building a large-scale road network on the moon, most likely we're doing it so that rovers can carry resources from point to point. They're going to need to recharge periodically, so having stations every so often to recharge rovers that also have emergency supplies for people, I think is a good investment.
Okay, let's see. Paul Shroom asked, lunar rails are rails or grooves? I don't really know what that means.
Rails or grooves. I know that this is kind of a pie in the sky thought, but there's enough iron in the soil that if you collect it, you can make iron rails as you go. So probably rails. Yeah, I know. Grooves would be possible too if you're using the bedrock or making your own slabs. I guess it's a question of, do you want to deal with making solid stone or concrete slabs, or do you want to deal with making metal rails and then anchoring them periodically? It just kind of depends on your resources and your available tech.
Okay. Any other questions for Chris? All right. Thanks a lot, Chris. Really appreciate it.
Everybody.